Okay, how do you prepare aldehydes and ketones? I'm going to go over this rather quickly because these are concepts that we covered already in class. The first set of reactions were reactions that were learned in chapter 12, and that's the oxidation of a primary alcohol to produce a ketone. So the first one is PCC, which is pyridinium chlorochromate, and CH2Cl2, which we abbreviate DCM sometimes for dichloromethane. The second one is DMP, which is the Des-Martin periodinane, which is also performed in dichloromethane. And the last one is a two-step process called the Swern oxidation. So the first step is using dimethyl sulfoxide and this molecule called oxalochloride, so oxalochloride, and then in the last step you treat it with triethylamine. So either one of those will convert a primary alcohol to an aldehyde. The next one is an ozonolysis reaction. So ozone followed by reductive workup with dimethyl sulfide, or DMS, produces two aldehydes in this case, and we went over an exercise in class that is in the book in chapter 8 where it shows you, if you erase the bond in the middle there, the double bond, and you put two oxygens. Anyhow, that's something that was covered in depth. So in this case, we end up with two aldehydes. What else? We talked about hydroboration oxidation of terminal alkynes. So using a large borane or a hindered borane, you can use R2BH to represent that borane, or you could use 9BBN. Another one that shows up in our textbook is dicyamylborane. The second step is treating that with hydrogen peroxide and sodium hydroxide, and of course that produces an enol which tautomerizes to give you the terminal aldehyde. So if you need to review that, that's in section 9.7 of our book. What else? If you want to make a ketone, you can oxidize a secondary alcohol. You can use a variety of strong or mild oxidizing agents. So I would accept many, different oxidizing agents. If you need to review them, do that. But the one that they've shown here is chromic acid. So that's sodium dichromate, sulfuric acid, and water. What else? If I have a tetrasubstituted alkene, in that case, when I do my workup after treatment with ozonolysis, instead of getting two aldehydes, I would get two ketones. And the reason why is because if you noticed on the last slide, these R groups that I've circled, they were not R groups, they were simply protons. So that's why in the previous slide, the previous ozonolysis slide, we got aldehydes, and now we get ketones in this case, so two ketones. Anyhow, what else? Another way to make a ketone is from a terminal alkyne. So this is a Markov-Nikov addition of water across the triple bond using mercuric sulfate, sulfuric acid, and water. And I told you this is a mechanism that isn't all that well understood. It proceeds through a tautomerization of an enol to give you a methyl ketone. So you end up with a methyl ketone in this case. So that's something to keep your eye on. So that's in section 9.7. So those are all reactions that we've seen before. And the last one is one that we just covered recently, which is the Friedelcrafts acylation. So if I take any kind of acid chloride and I treat that with aluminum chloride, so as an acid chloride with a Lewis acid aluminum chloride, I can do the Friedelcrafts. And aromatic rings that are not too strongly deactivated will react with an acyl halide with a Lewis acid. And we talked about deactivators that don't permit this reaction to occur. So that's something that should be relatively fresh in our mind. So we could do these questions really quickly. I mean, to oxidize a secondary alcohol to a ketone, I mean, choose whatever you want. You could put PCC, you could put Des-Martin periodinane, you could do the Swern reaction. Let's practice the Swern reaction, which is dimethyl sulfoxide, oxalochloride in the first step, and then triethylamine. What about the next one? You want to convert a primary alcohol to an aldehyde. So any kind of mild oxidizing agent, why don't we choose PCC? That's always a crowd favorite. There we go. So pyridinium chlorochromate. For the next one, we have a terminal alkyne and we want to make a methyl ketone. So notice this is a methyl ketone. So for that one, we would use sulfuric acid in water with HgSO4, so mercuric sulfate. There we go. And of course, you should be able to draw the intermediate. So what would you get in this case? You would end up with this enol, of course, which would tautomerize to give you the ketone. And the next one, I would use 9-BBN. 9-BBN in the first step. And in the second step, I'd use peroxide, hydrogen peroxide, and a base. And of course, you should be able to draw the enol for this one too. Let's give it a try. So for this one, I end up with an enol with the hydroxyl on the end, and of course that would tautomerize to give me the aldehyde. So there we go. Those are some oldies but goodies. All right, so nucleophilic addition reaction. So as you can imagine, the carbonyl carbon is quite electrophilic, and there's a couple of good reasons for that. Number one is resonance. So we could draw a resonance structure where we put the negative charge on the oxygen, which gives us a carbocation. So it's pretty obvious that that would be a good electrophile. And then, of course, what we like to draw in class when we're drawing our mechanism is we draw the dipole in between carbon and oxygen. So oxygen has an electronegativity of about 3.5 and carbon is around 2.5, so that's a delta of 1.0, which is considered a polar bond. Generally, anything above half a unit is considered polar. So that renders that carbonyl carbon quite open to nucleophilic attack. So as you can imagine, we're going to look at some reactions that occur at carbonyl carbons in this chapter. So what's the hybridization of the carbon on the carbonyl of an aldehyde or a ketone? Well, you probably guessed it, it's sp2. So what the molecular geometry would be is trigonal planar. So it's as flat as a pancake, and that's why they've put it on this what looks like a piece of glass or something, or a window. Anyhow, they have the ketone in this case. They're trying to show that it's flat, but after a nucleophile attacks that carbonyl, right, because of the dipole, so we could draw in our delta plus and our, oops, that doesn't look very good, and our delta minus, we end up producing something that's sp3 hybridized, and therefore the molecular geometry goes from trig planar to tetrahedral. But in this slide, it shows the nucleophile attacking from the top face of the molecule. But if you're asking yourself, well, could it attack from the underside of the molecule? So could it attack from the underside like that? Of course it could. So it's not going to discriminate between either face of the molecule, and that's going to be important with respect to stereochemistry. All right, so aldehydes and ketones. What about the reactivity of aldehydes versus ketones? Which one's more reactive? So it says aldehydes are in fact generally more reactive towards nucleophiles, so they're better electrophiles than ketones. There's a couple of reasons for that. The first one is steric effects. So if you think about it, an aldehyde is flanked by an alkyl group or an aryl group and a proton is going to be smaller than two alkyl groups. So the first one is just sterics, it's just less sterically hindered. And the second one is electronic effects. If you remember, our groups are electron donating, so they're going to pour electron density into that positive charge and stabilize it, whereas the aldehyde only has that stabilizing effect occurring on one side of the carbonyl carbon. Thus, it's going to be more electropositive and more open to attack from a nucleophile. So some nucleophiles require acidic conditions, others require basic conditions. So here's an example, the Grignard reaction. So this is a reaction you should be familiar with. It requires basic conditions because not only is methyl magnesium bromide that they've shown here, not only is that a good nucleophile, but it's also a very strong base. So it's the conjugate base of methane, which has a very high pKa, and I told you in class that you could draw the methyl, you could draw it like a carbanion, even though it's probably not exactly like that. So you can draw it as a nucleophile, and you could do your nucleophilic attack like that. But something else that we talked about with respect to Grignard reagents was that they're going to be destroyed in the presence of water. And why is that? It's because not only is the Grignard reagent a strong nucleophile, but it can pull the proton off of water to produce hydroxide. So it has to be done in basic conditions. So of course, after you do the nucleophilic attack, of course you have to throw in water or some kind of source of protons to produce an alcohol. So we go from a ketone in this case to an alcohol. So there's Grignard chemistry. And in fact, just to back up, Grignard chemistry, the reason that you can't do it in basic conditions is why you can't do it in the presence of an alcohol. And that's why we discussed protecting groups back when we learned about the Grignard reaction. So if you remember TMS chloride and making it a silyl ether, that's what that was all about. So, nucleophilic addition reaction. So under basic conditions, so we have a couple of mechanisms to look at now. So this is under basic conditions, all nucleophiles react with carbonyls by the same general mechanism. So if it helps, if you need to draw the dipole in every time you take a look at this, go ahead, do it. So I have my negatively charged nucleophile because I'm in basic conditions, so it's not going to be protonated. It's going to nucleophilically attack the carbonyl, and then I end up producing this tetrahedral or sp3 hybridized carbon here. And then a proton transfer occurs at the end to produce an alcohol. So the nucleophile attacks, you get a negatively charged intermediate, and then it's protonated upon acidic workup. So that would be step 2. There we go. So it says here, aldehydes and ketones can react with a weaker nucleophile. So a weaker nucleophile, what's a weak nucleophile? Maybe water, maybe an alcohol. Under acidic conditions, by the same general mechanism, I would say a similar mechanism, but the first step is going to be different. So the first step in this case, in acidic conditions, we're going to use our acid to protonate the oxygen on the carbonyl. So now we have a positive charge on our carbonyl, and yes, you could probably all draw the resonance structure. I'm not going to draw the curved arrows, but you could probably all draw this, right? So that shows you that that carbon is very, very electrophilic, even more electrophilic than the carbonyl that we looked at in basic conditions. And so it's going to be open to nucleophilic attack by weaker nucleophiles. So there we go. And let's see, what do we have next? So that's acid and base conditions. So acidic conditions are required in order for a weak nucleophile to attack a carbonyl carbon. So a weak nucleophile is not going to just attack carbonyl unless the carbonyl is protonated, because then it becomes a much better electrophile. It's a much stronger electron seeker because it's going to have an actual positive charge shared between the oxygen and the carbon, shown in those resonance structures. All right, where am I? So, when a nucleophile attacks a carbonyl group, the equilibrium depends on the ability of the nucleophile to function as a leaving group. So, it says here, if I have a ketone and I treat that in hydrochloric acid, I can add chloride and a proton to the molecule. And it says here, since the nucleophile chloride is also a good leaving group, the equilibrium favors the ketone in this case. All right, and we are going to cover the following nucleophiles and the reactions with aldehydes and ketones. So you can see here, there's a lot of different nucleophiles. So first you can see oxygen nucleophiles. We're going to have water and an alcohol or alcohols, and then this molecule here you might recognize, this is ethylene glycol, so that's a diol. Then we're going to look at other sulfur nucleophiles, nitrogen nucleophiles, and of course hydrogen nucleophiles. If you're wondering about the aluminum hydride, yes, that comes from lithium aluminum hydride, and the borohydride comes from sodium borohydride. Then of course we've got our Grignards. So Grignards here, this is a cyanide, and something else that's kind of fun that we're going to look at is this guy here, and this is called a Wittig reagent. So Wittig is a person's name, Wittig, named after Georg Karl Wittig. Anyhow, so he discovered a new way to make carbon-carbon bonds, which is a really interesting chemistry. So we'll take a look at that in a little bit. And this is the end of part 2.